Hi guys, this is Nakoda and welcome back to All Things Physio. Today I will be going through a scenario question to basically put into practice what we've been learning in the videos before. So we're gonna go through this, apply the principle of moments, apply calculating perpendicular distances, and see how far we can get, what we understand from what we don't understand, and basically build on the knowledge that we already have, right? So in the scenario, it says, let's assume that you're a physiotherapist and you've been treating a patient that had a quads injury. After a few weeks, you decide to introduce strengthening exercises. You give the patient leg extensions with a 15-pound weight on his ankle to add resistance. So this is what they want us to calculate. Now, because there's so much parts to calculate in this question, it will be split into two videos, right? So I'll let you know that from the start, right? So they asked us to calculate the exterior moment with 15 pounds, with the 15-pound weight at the ankle at the angle of 30 degrees, 45 degrees, 90 degrees, and 0 degrees extension, and the quads force necessary to maintain each position. Now they gave us different values here. So they told us that the weight of the shank and foot is 40.3 newtons. The length of the shank and foot is 28.3 centimeters. Now we know that we don't work in centimeters for moments, and we work in meters, so we'll have to convert that. They gave us the conversion from pounds to newtons because you know that we have to have the force in newtons, and they gave us the quads moment arm. Now from the start we could see that we don't have to calculate the perpendicular distance here because they already said moment arm. Remember, once they say moment arm or lever arm, this is the perpendicular distance. But what we have to do is convert the cm to meters, right? So let's do our conversions. Okay, so the length of the shank and foot in meters, 1, 2, would be 0.285 meters. For this, you would see that 1 pound is equal to 3.29, but they gave us 15 pounds, so we need to calculate that. So 15 pounds would be equal to 15 by 3.28, which is equal to 49.35 newtons. And the quads moment arm, we could do this later down, but we'll do everything one time, would be converted to 0.038 meters. So now that we have done that, we could kind of start to visualize the question and apply the knowledge that we know about moments and calculating perpendicular distance, all of that good stuff. So the first part, part A, is 30 degrees. So part A, 30 degrees extension, right? So now what we can do is draw a diagram to understand what's going on, right? So we could put here a block or a chair, whatever it is, and this would be the person's quadricep, and their foot would come down here, and we've placed a 15-pound weight, or we calculated over here that the weight is actually 49.35 newtons, right? So what the question is telling us that the patient is doing leg extensions. So that would mean that the leg will be moving out this way. It would be extending, right? So for the first one, like we said, it would be 30 degrees extension. So we can draw this diagram and we could adjust it to what the question is telling us. You have the patient's quadriceps, you have their knee, and then this is where their foot was, but they have gone outwards. They have extended it 30 degrees, right? So now we have 30 degrees extension. So from this, we can see what's going on. We can calculate the exterior moment. Now, remember, to calculate moments, it is force by perpendicular distance, right? So we don't have the perpendicular distance. What they gave us in the question was the length of the shank and foot. Now, the shank would be like the shin area, the anterior portion, and the foot would be this area here, right? So they gave us the length of the shank and foot that we calculated. So that would mean that this length here is length of shank and foot 0.285 meters, right? What else they give us? They give us the weight, so we know that the weight acting downwards, we could just cover that there, the weight acting downwards, and this is 49.35 newtons. They also gave us the weight of the shank and foot, right, which is 40.3 newtons. So we realize that we have two forces, right, but one distance. So what we have to do is find the moment of these two forces, right? So first we could do the shank and foot. That would be the abbreviation we're using for shank and foot, right? So we know that they told us that the length of the shank and foot we're working with is 0.295. Now from this diagram, we could get our triangle. To calculate our perpendicular distance, we can do what? Extend the line from the line of action of the force, to the fulcrum, and we realize that it's perpendicular there, right? So we can send this triangle over here, and what would we get? We would get this, right? We know that here is perpendicular. We know that the length of the shank and foot is 0.285 meters, right? And we want to calculate the perpendicular distance, which in this case would be D1, because we're dealing with the first force, which is the shank and foot. So we'll put F1, right? So what we do is that we can label our triangle. We know that here is 30 degrees. So here would be what? The total interior angle of a triangle is 180. If this is 90 and this is 30, then this would have to be 60. Now we could label our triangle. We could put B here, probably A here, but we know that the longest side have to be C. Now from the last video, we know where we're going from this. We can use sine rule, to find the perpendicular distance. And sine rule says A over sine A is equal to B over sine B, which is equal to C over sine C. Now which one we want to use? We want to find B, because this B here would be the same as the perpendicular distance D1. Remember, we draw the line here and we know that there's the perpendicular distance we want to find. So we could use this, and they gave us C, so we can use this. So going further, we would see that B over sine B is equal to C over sine C. Now we could kind of plug in values, right? So B, we know we could change it to D1, because we know that is the perpendicular distance we're trying to find, over sine. Now since this is B, the opposite angle would be over here, so that would be sine 30 is equal to C, which is 0.285 over sine C. Now since this is C, we know that this angle would be C, sine 90, right? So we can what we could do here, cross multiply, and we'd get D1 sine 90 is equal to 0.285 sine 30. And we'll get D1, or the perpendicular distance for the shank and foot, is equal to 0.285 sine 30 over sine 90. So we could calculate that now, right? So sine 30 is 0.5 by 0.285, and we'll get 0.1425, and we know that sine 90 is 1, so our perpendicular distance for the shank and foot would be 0.1425, right? So what we could do is actually find the moment of the shank and foot, right? So we just plug in into this equation here. So the moment for the shank and foot would be equal to the force, which is the weight of the shank and foot, 40.3 newtons, by the perpendicular distance, which is 0.1425, and we would find that the answer is 5.742, right? So we're leaving it to 3 decimal places for now. Then we would put it to 2 decimal places. So now we can actually find the moment for the weight at the ankle, right? So we're going to do the same thing. So moment M is equal to, this is your second force, so this will be F1, this would be F2, right? So that'll be F2 by perpendicular distance 2. Now what you realize, because the question did not say that there is a center of gravity of the weight, meaning that that would be where all the weight acts downwards, it would mean that this weight here would be distributed straight throughout the leg. That is why we could have used 0.28 for the length of the shank and foot, right? So now that the ankle weight is on the ankle, the distance would be the same. Try and get me. We're gonna draw the triangle again, and we're going to realize that the ankle weight is at the ankle, so it would be the same distance away from the fulcrum, right? So we realize that if we draw this triangle and we put 0.285, and this is perpendicular, this would be D2, this would be 30 degrees, this would be 60, you realize that you have the same triangle here, right? Because the distance at which each force is acting is the same. So the foot, the weight of the foot is acting at the same distance from the fulcrum as the ankle weight. Try and understand what I'm saying. So this is the patient foot. The weight is acting at the distance they gave us, which was the length of shank and foot, which would be 0.285 meters from the fulcrum, and the weight is acting at the same distance. So in this case, because they did not give us a center of gravity, and the distance from the center of gravity, from the fulcrum, this would be using the same distance, right? So we'll get the same thing. We could go through and look at it, right? So use the same sign rule. We'll get back this. We're using, okay, let's label everything again. This would be A, this would be C, this would be B. And so if we use the same thing, B sine B is equal to C sine C, we would get now, when we transfer the values, or we substitute the values, we'll get D2 is equal, D2 over sine 30, because, you know, B, this would be B, this would be C, is equal to 0.285 over sine 90, right? So you realize that this and this is the same thing. So we can therefore assume that D2 is the same value as D1, which is 0.125. However, the moment would be different because the force is different, right? So the moment would be using F 2, which would be 49.35 newtons, by D2, which would be 0.1425, which is equal to 49.35 by 0.1425 is equal to 7.032, right? So we have found the moment of the shank and foot, because this was one of the forces acting, the weight of the shank and foot, and we found the moment of the 15-pound weight, right? Now what we realize is to find the total external moment, we would have to add these two. That makes sense, right? So what we can say now is the total exterior moment is equal to F1 by D1 plus F2 by D2. That makes sense, right? So we have found both of the moments. Would that be 7? We didn't put in units. Remember, moments is in Newton meters. All right, 5.742 Newton meters plus 7.032 Newton meters. And we get 5.742 plus 7.032. We would get 12.774 Newton meters. So that is the total exterior moment for the 30-degree angle, right? But the question goes further and asks us for the quads force necessary to maintain each position. So we need the quads force necessary to maintain this 30 degrees with the ankle weight, right? So we know that the principle of moment states that the sum of clockwise moments is equal to the sum of anti-clockwise moments, right? So we're saying that this exterior moment, remember we're moving in this direction, that would be anti-clockwise. So we know the sum of the anti-clockwise moments is 12.774 Newton meters. So the sum of the anti-clockwise moments is equal to 12.774 Newton meters. So that would be the exterior moment or the anti-clockwise moment. And since we know that both of them the same, we can assume that the clockwise moment is equal to the same thing. It's a fact actually. Once it's the same, it'll be the same thing, right? Now what is producing the clockwise or the interior moment, right? It's the quads, because the muscle that is responsible for leg extensions is the quadriceps muscle. This muscle extends the knee, and the quadriceps muscle pulls this way, right? Now this muscle therefore would be the muscle that helps to maintain each position. So this muscle must generate a force now to hold this leg in this 30-degree position, right? Now they gave us the quads moment arm, and now they want us to find the force. So we know that the principle of moment states that, well, we could do that. We'll do it right here, right? The principle of moment states the moment is the product of the force by the perpendicular distance from the point, right? So they gave us the perpendicular distance of the moment arm. Take it in, it's a moment arm. So they gave us the perpendicular distance of the quad, and it was, so what we could do here, so we figured out the clockwise or interior moment, and we're saying that it was 12.774 Newton meters. They want us to find the force, but they gave us the perpendicular distance as 0.038 meters. So what we can do, we can transpose this formula so that force would be equal to the moment over the perpendicular distance, so that would be 12.774 Newton meters over 0.038 meters, so that would be divided by 0.038. The force would be 336.16 Newton meters. So the quadriceps would need to generate a force of 336.16 newtons, my bad, newtons, in able to keep the leg in this position.